We have three new quantities to talk about: kinetic energy, potential energy, and work. Work is not an energy, but it's a change in energy. And kinetic and potential energies are the actual energy. We'll start by talking about work. And it's a good name for a change in energy because it literally is getting stuff done. We can get a number for the work accomplished by multiplying force and displacement. Work requires a force, and it requires the force to move something. If the force moves something, you can say that the force did work on whatever it moved. And the product of that force and how far that movement was is the work that was done. I'm going to illustrate later what I mean by the displacement and the force are in the same direction. They can be in opposite directions, but they can't be perpendicular. Let's put this little equation to work. Force, no pun intended, force times displacement. So you apply a pushing force of 100 newtons to something. So we'll just stick with the box sliding on the floor. And you slide it 10 meters, delta x. The work that you did on the box, and I'm choosing the words carefully there, the work that you did, you the pusher, on the box, the recipient of your energy, is force times displacement. 100 newtons of pushing force times 10 meters of displacement. That's 1,000 with units in joules. Let's abbreviate joules with a capital J. But you know, if you push something across the floor, you've got some resistance to overcome. Don't make the assumption that you're the only one involved in that box is moving across the floor. You may be applying a pushing force, but something is also applying a force and it's not helping. Friction resists with a force of F sub F. The box moves, it moves this distance of delta x, but only you made it happen. Friction was no help at all. Let me play out a little narrative here. According to you, my work on the box is the pushing force times the displacement delta x. Friction will reply, yeah, well, I did work too, and it was minus the friction force times the displacement delta x minus. Where does that minus come from? The friction force is in the opposite direction that the box moved. When the force and the displacement are in opposite directions, the work is actually negative. What does that really mean? That means friction robbed the box of some energy. Friction was like a bandit, and it took some energy away from that box. So the work it did on the box was negative. It was counterproductive. The displacement and the force are in opposite directions, so the displacement is in the positive direction and the force is in the negative direction. And it shows that way in this picture here. So you could say the friction force is some negative number. Now if you're the box, what you're going to say to you and friction is stop fighting. Cooperate, please. Get me from point A to point B. You two aren't doing it together very well. The box doesn't see F sub P delta X of work being done on it. According to the box, the work done on it is your push force times displacement minus that annoying friction force times displacement. And so the box just wants you guys to work together, not to work against each other. Problem is that will never happen. You and friction do collaborate, but not in a helpful manner. You combine to provide a work that's smaller. So the net work, not the network, the net work is the work that you do on the box plus the work that the force of friction does on the box. Work of friction is subtracted from the work of you. Let's put some numbers on this right away. So you apply a 100 Newton force to that box. And friction is busy resisting it with a minus 100 Newton force in the opposite direction. But you do manage to slide the box 10 meters across the floor. Okay, how does that work? You apply a force of 100 newtons and friction totally resists it with its own 100 Newton force in the opposite direction. How does that thing move? Remember Newton's first law. Force changes motion. It doesn't cause motion. Force is responsible for acceleration. You have zero net force. If you apply 100 newtons one way and friction resists with 100 newtons, there's no total force. It's zero. But that's okay. The box can move, but it's going to move at constant speed. And this is how you normally do things. You got to push a box across the floor. Usually you do it such that you move at constant steady speed across the floor. Your brain is a very powerful computer. It controls this very well. So the work that's done on the box as it moves this distance delta x is the force of U, 100 newtons times that displacement, plus the force of friction, minus 100 newtons, times that same displacement. The work is force times the displacement over which that force acts. And certainly for that entire 10 meters, you were applying the push force and friction was applying the resistance force. Those cancel. 100 times 10 minus 100 times 10 is 0. So yeah, 0 net work was done. Nevertheless, the box moved. Now this is more brain teaser for us here. How is it that the box moves when there was no net work being done on it? Work does not correspond to the box moving. It corresponds to the box's motion changing. So on this box, there are two forces acting, U and friction. And the net force is the sum of the two, 100 newtons plus a negative 100 newtons. So there's 0 net force on this box. There was no net work because there's no net force. Just remember, no net force does not mean nothing moved, because force causes acceleration. It doesn't cause motion. You have 0 net work because you have 0 net force. Our method of calculating work should really be revised slightly. Instead of just saying work is force times displacement, let's say the net work is the net force times displacement. So take all of the forces, in this case pushing and friction, and add them together, multiply them by the displacement, and that is the total work that was done on the box. What is the other consequence of there being no net force? Think Newton's second law, F equals ma. And it's not just F, it's the net force. So if there are two applied forces like pushing and friction, you have to add them together, and that equals the mass of that box times the acceleration. So if there's no net force, there's no acceleration. So I just put in one very abrupt statement. No net force, no work. No work, no acceleration. If any one of them is 0, all three of them are 0. You go at steady speed. It doesn't mean 0 speed. 0 acceleration means constant speed. If you have 0 acceleration, the energy of motion doesn't change. That's why we call it the energy of motion. If you don't change the motion, you don't change the energy of motion. Kinetic energy is a constant when there's no work, no net force, and no acceleration. If there is a net force, then F equals ma, there is an acceleration. And if there's an acceleration, then speed is changing. And if speed changes, your energy of motion is going to change. So the kinetic energy changes if there is a net force. That's a very important principle. It's called the work energy theorem. That if there is net work, then there will be a change in kinetic energy. So if you can calculate the net work done, force times displacement, that equals the change in kinetic energy. If you push a box across the floor at constant speed, the kinetic energy doesn't change, and there is no net work being done. This is actually the definition of work. Let's put some numbers on this right away to get it solidified for you. Apply 100 newtons to that box. Now we give that box a mass, 20 kilograms. Now we say friction is resisting with minus 50 newtons instead of 100. The box slides 5 meters across the floor. The net work done on the box is the sum of the work that you do pushing it and the work that friction does resisting it. Very important to remember that friction is resisting the motion, therefore its work is negative. It is robbing the box of energy that you are putting into it by pushing it. The net work is your 100 Newton force times that 5 meter displacement plus the friction's minus 50 Newton force times the 5 meter displacement. So it's always the force times the displacement over which that force is acting. And that comes out to 250 joules. That is also the change in kinetic energy of the box. So in this case, where you push with 100 newtons, friction resists with 50 newtons, the box will accelerate because you are pushing harder than you have to. The only time the box doesn't accelerate is if you push with the same 50 newtons that friction is offering. But you're overpowering friction by 50 more newtons. So the box will accelerate, and therefore its kinetic energy will change because it's gaining more speed. Let's find that acceleration. You can do that because you know what the net force is, and net force equals ma, and the net force is U plus the friction, and you are applying 100 newtons, friction is applying minus 50 newtons. The net force is 100 minus 50. The net force is 50. And the mass is 20 kilograms. This acceleration is net force over m, right? If F equals ma, then A is F over m. 50 newtons, mass is 20 kilograms, the acceleration is 2.5 meters per second squared. So as you push that box, it's going faster and faster and faster. It is gaining motion. It's gaining energy in motion. It's gaining kinetic energy. That gain in kinetic energy equals the net work done pushing that box. Let me remind you of what we learned in the first part of the semester and show you how all physics is cumulative. It's a worthwhile question how long it actually takes to push that box 5 meters. That is entirely a kinematic question, right? Because you have an acceleration. You have an initial velocity. Make a list of knowns. You know the acceleration, you just calculated it, 2.5 meters per second squared. You know the initial velocity, it's given, 0. And you want to know time. So you don't know time. So you ask yourself, which one of those kinematic equations of motion takes initial velocity and acceleration and displacement of 5 meters, third thing you know, and gives you time. Pause the video if you need to and look at the kinematic equations of motion and ask yourself which one works. Okay, did you pause the video? What do we call that again? Displacement is 1/2 at squared. Do you remember the name of that equation? I just said it. It's the displacement equation. In its full glory, the displacement equation is displacement is initial velocity times time plus 1/2 times acceleration times time squared. But the initial velocity is 0. 0 times anything is 0, so you can just leave that out. So whenever you start from rest, you can say displacement is 1/2 at squared. Acceleration is 2.5. Time is what we want to know. And we know that delta x is 5, so I write it this way. 1/2 a t squared equals 5 meters. And solve this. 0.5 times 2.5 times t squared equals 5 for time. And you get a time of 2 seconds. Make sure you can perform this algebra. And that's how long it takes to push this box 5 meters. You push pretty fast because 5 meters is a long ways to do in 2 seconds. So we're going to come back to this example later. Once we introduce kinetic energy, we can take this example one step further and ask, how fast is the box moving after these 2 seconds are up? And we can answer that question 2 different ways. You could answer it with the old-fashioned way right now. You have an acceleration of 2.5. You have a time of 2 seconds. You have a displacement of 5 meters. I mean, you have more information than you need to calculate the final velocity. Go figure out the final velocity using basic kinematics. We'll also get that exact same answer using the work energy theorem after we have defined a way to calculate kinetic energy.